In our previous videos, you met our chickens and saw some of the eggs that they laid. Today we're asking a question about these eggs. We're asking, what is the volume inside one of these eggs? And what you'll notice is that every egg is a slightly different size, so I would actually expect the volume to always be a little bit different. So what we really want to ask is, what's the average volume in some idealized, perfectly average egg? And I can't do that by finding the volume of one egg individually, but what I could do is crack a bunch of the eggs and average them, and that would give me a good estimate. And so today we're talking about a method of estimating that perfect average and a process of approximating that estimate using what we call confidence intervals. So I guess we got to start by cracking some eggs. So there you go, that was 20 eggs, and we saw that it landed right at 1 liter. So now we know the average volume of an individual egg. We're going to have to estimate the standard deviation of the volume of an individual egg, but from that, we can create our estimate. So let's go see how to calculate that estimate. So we're asking, what is the average volume of an egg? A good place to start is with an estimate. So what if we give an estimate for the average volume? Well, that would be pretty simple. We would just take our total amount, which was 1 liter, and divide it by the number of eggs, which was 20 eggs, and that turns into 1/20th of a liter, 0.05 liters, or probably better to say 50 milliliters. So that's a good estimate. But notice, this isn't a great estimate because someone says, well, if this is an estimate, how close is the estimate? Well, I wouldn't know that. So what would be better than giving an estimate? Well, better than giving an estimate would be to give a range of values in which I'm pretty sure that the average volume of the egg lands in here. So what if I were able to say something like, I know the average egg is between 45 and 55 milliliters. That'd be better because then I'm no longer just giving a guess, I'm giving a range of values where you could expect the answer to be. But then someone might ask, well, how accurate is that range that you just came up with? And that brings us to the best possible way that we could give an estimate, and that is to give the probability that the average volume falls within that given range. So the best comment I could possibly give would be to say something along the lines of, I'm 90% confident, or there's a 90% chance that the actual volume of an egg lands between 45 and 55 milliliters. And we've given an estimate, we've given a range of values that's reasonable for that estimate to fall within, and we've given a probability of the likelihood of falling within that estimate. Well, that's exactly what we're going to do today. And we're going to start by thinking of it as a number line, and then putting our estimate on that number line. Once we have our estimate, we're going to create error bounds. And so the error is how far away from that estimate we think we can reasonably be. We'll put error bounds on both sides of our estimate, and then what we'll do is we will figure out the probability of being within those error bounds, called the confidence interval. We'll actually work backwards a little bit. We'll start with our goal probability and use that to figure out how big we want our error bounds to be. So if you think, what is this range going to be? It's going to be the average, which is our estimate, which is x bar. And then we'll have our error bounds, which are e. And notice that we'll get this mark over here, which is x bar plus e. And then we'll have this mark over here, which is x bar minus e. So once we've calculated our error bounds and our estimate, we have our confidence interval, which is this range of values given right here. A range of values from A to B is a C% confidence interval if you're C% confident that the true value lies within this range. Let's talk just a second about what I mean by true value. Well, notice earlier we had a lot of eggs. Every one of them has a slightly different volume, but there's some true average volume that's true for all eggs. So in other words, if I could somehow crack an infinite number of eggs, there would be an average volume for that value. That's what the true value represents. But there's no way of knowing what the true value is, but we would say that there's a C%, in our problem today we'll do a 90%, we'd say that we're C% confident that the true value falls somewhere within this range of values. Now you notice what we need is we need a really good way to calculate this error bound, or what E is. In order to do that, we need to combine two ideas. The first is that of a z-score. You'll remember this from earlier in the semester, that our z-score is z equals x minus mu over sigma, where mu and sigma are the average and standard deviation of a normal distribution. But let's combine that with what we just learned about the central limit theorem. The central limit theorem says this average should always be normal, and that the average of the averages should be equal to mu, and the standard deviation of the averages should be equal to sigma divided by the square root of n. Well, if we put those two together, what you'll see is that z should equal x bar minus mu divided by sigma over square root of n. Notice I just replaced my x with x bar. My mu stayed the same because my average for my averages is still mu, and my standard deviation changed to mu divided by the square root of n. Now we take this and recognize that this should be a normal distribution. This means we have a normal curve, like we've seen throughout the semester. And if we use this expression, we end up with a standard normal curve. So that means the mean and the standard deviation for this curve are 0 and 1. So if we want to create some sort of confidence interval, what we're looking for is a range of values where the probability within is whatever percentage we're looking for. We're going to call this value ZC, and then this is going to be the opposite side, and it's going to be negative ZC. And then in here is whatever confidence we want to have. So if we want a 90% confidence interval, then we're going to make this shaded area equal to 90%. If we want 99% confidence interval, we'll make the shaded area equal to 99%. So notice this gives us an inequality. It says that negative ZC is less than, this expression is less than positive ZC. Do a little bit of algebra, and I'll let you do that on your own, and we end up with our equation. X bar minus ZC times sigma over square root of n is less than or equal to mu, is less than or equal to x bar plus ZC times sigma over square root of n. This is a pretty important formula, so I'm going to put a big box around it. And I'm going to encourage you to write this down, and you're going to want to learn this because we're going to use this over and over and over again throughout the semester. So back to our problem. Suppose I want to create a confidence interval for the eggs, for the volume of the eggs that I just saw. Well, you'll notice my formula has 4 pieces. It has x bar, it has sigma, it has n, and it has zc. And so what I need to do as the person solving the problem is simply go and figure out what these 4 values are. If I can find these values, then I can put them in my formula and come up with my confidence interval. X bar is simply the average, and notice we've calculated this earlier. It was simply 1 liter divided by 20 eggs, which I turned out into 50 milliliters. Sigma is a number we have to be told or given to us outside our problem. And for this case, I'll just tell you that sigma for this problem is roughly 8 milliliters. We'll talk more about sigma and how well we can know this number during class. N is the number of measurements we've taken. In this case, N is equal to 20 because we used 20 eggs. Now, ZC is the number that requires a little bit of effort. So ZC, if you remember, is the value that if I draw my normal distribution, makes the area in the middle equal to whatever percent I want. So if I want a 90% confidence interval, which is what we're going to work with today, then that means this middle part needs to be 90% or 0.9. So in order to find this value, we'll need to go into our calculator and use the inverse normal command. If you're on your TI, it's the INV-NORM command. And if you're on your ClassCalc app, you're going to go to the normal distribution. Then you're going to go back in and you're going to add the inverse CDF onto the end of it. Okay. But once we have these things, we need to know what the area is that we're talking about. We need to know what the mean is that we're looking for. And we need to know the standard deviation that we're using. So our area, it's tempting to put 90%, but remember how our inverse normal command uses. Our inverse normal command gives us all the values to the left of whatever term we're talking about. So we don't just want to put 90% because the area to the left of our value is 90% plus 0.05 plus 5% or 0.05. So we actually want to use 0.95 for our area for this command instead of 0.9. For our mean and standard deviation, notice our problem is a normal distribution. We're using a z for a standard normal distribution. So z tells us that our mean is going to be 0 and our standard deviation is going to be 1. It's really tempting to go use the mean and standard deviation from earlier in our problem, but what we've done when we've used this formula, we've converted everything to a standard normal distribution. And so 0 and 1 are the values we're going to use. And really, throughout most of these tests we're going to do, we're always going to use 0 and 1 as our commands. So we put this in our calculator, and we end up with our final result. And our final result is that ZC is 1.644. Okay, so now that we've found all our values, we're ready to put them in our formula and see what comes out. So we take these numbers, our x bar, our sigma, our n, and our ZC, we put them in our equation, we type them in our calculator, and see what number we get. So as we type these in, we get 50 minus 1.644 times 8 over the square root of 20 is less than or equal to mu is less than or equal to 50 plus 1.644 times 8 divided by the square root of 20. Typing this all into my calculator gives me 47.06 is less than or equal to mu is less than or equal to 52.94. So what does that mean for our eggs? What's our final conclusion? Remember that our average value was 50 milliliters, which I'll put here in the middle of our number line. And what this interval says, what this confidence interval says, is that there's a 90% chance that the actual average, if we were to do an infinite number of eggs, falls within this range. So there's a real average, and I'm 90% confident that I captured it between the values of 47.06 and 52.94. So if somebody were to come ask me, hey, what's the average volume of an egg that your chickens lay? I could say with 90% confidence that it's between about 47 and 53 milliliters. And notice this is a really good response because it gives them an estimate, a range of values that estimate is going to fall within, and a percent that I'm confident win. I'm not guaranteed to have my value within this range because there is a 10% chance that my range is either too high or too low and the actual average falls outside of it. But for most practical purposes, and especially for the purposes of measuring volumes of an egg, 90% confidence is sufficient. But we'll notice there are some cases in life where you need to be more confident. If that's the case, we just create a 99% confidence interval or a 99.9% confidence interval. And we do that by going through the exact same thing and changing what this ZC term is going to be. And that will change our interval and give us more confidence that we know the true volume or the true average that we're looking for. Well, now we know a little bit about confidence intervals. We know a little bit about how big our eggs are. And most importantly, now if someone asks me the volume of an egg, I can give them with confidence a range of values that tells them what the volume of that egg is. Look forward to seeing you in class. Thank you.